Hi, I'm Peter Schurtenberger and I'm a member of the Division of Physical Chemistry at Lund University. At Physical Chemistry we have a research unit with about 12 professors and their research groups that is entirely devoted to soft matter. This provides an ideal research environment for the users of EUSMI, because while EUSMI is about infrastructure, it's also about science. And with this very broad soft matter background at Physical Chemistry, we can help the users of EUSMI to not only plan and make their experiments under perfect conditions, but we can also help them to understand their often very complex systems. One of the specialties here at Physical Chemistry is the use of scattering methods to characterize soft matter. Scattering is an ideal method to characterize soft matter because it's non-destructive and provides an in situ characterization. In particular, light scattering has been used frequently for this task. However, light scattering can only be used normally for ideal solutions that are in particular highly transparent. This is not the case in many of the samples that are, for example, of industrial interest, and therefore light scattering has not really been used much for this task. At Lund University, we now use a technology that also allows us to characterize highly turbid samples. This uses the so-called 3D cross-correlation technique that suppresses all multiple scattering contributions from such turbid samples. And this means we can also measure with light scattering samples that are as turbid as undiluted milk. Such a technology is implemented in this instrument that uses a goniometer with a detector in order to scan the scattered light from either transparent or fully turbid samples at different scattering angles. With that we can do static and dynamic light scattering and characterize structural properties and diffusion of particles up to, for example, very high concentrations in turbid colloidal systems. Sometimes these samples are not even stable with time. They may undergo an aggregation process or may show phase separation. This requires, for example, that we can then do these measurements in a time-resolved fashion to characterize these non-equilibrium processes. This is possible in this next instrument, which is a home-built adaptation of this cross-correlation scheme that uses different detectors at different angles and therefore allows us, within a very short time, to measure at different angles and do this then in a time-resolved manner. Sometimes, however, these samples are so turbid that there is actually no single scattered light left. And then we have to do something different. What we can then do is so-called diffusing wave spectroscopy to learn much more about the dynamics or, for example, about the viscosity and the viscoelastic properties of these highly turbid complex samples. This is shown in this particular instrument where EUSMI users can do things like DVS-based microrheology. They can measure diffusion of emulsion droplets or look at the motion of colloidal particles as they undergo a salt-shell transition. Sometimes, or actually most often, soft matter is really what we call multi-scale. That means we have to characterize these samples on many different length scales. With normal light scattering, this is no longer possible. And so therefore we have at Lund University also an ultra-small angle light scattering instrument with which we can do static and dynamic light scattering at ultra-small angles and therefore characterize soft matter also on very large length scales. These length scales actually extend all the way down into the length scales that are normally visible also with optical microscopy. One example is studied here, where we look at the evolution of a soft gel that is formed by aggregating responsive or you could also say intelligent particles. And with ultra-small angle light scattering, we can now measure and characterize the characteristic structure of these very interesting soft gels. In many systems that are studied by EUSMI scientists, we also want to get information on much shorter length scales that are no longer accessible by light scattering. This requires the use of X-rays, for example. At Lund, we also offer access to a state-of-the-art small-angle X-ray instruments that then provides us with the missing information down to length scales that are almost approaching atomistic length scales. You see here our instrument where we can study liquid and solid-like samples and cover all the length scales that are coming from light scattering down to these near atomistic resolution structures. A particular specialty here at Lund University is that we not only offer one particular type of technique, but since soft matter is often very complex and requires a multitude of instruments, in order to understand the behavior of these systems, we offer a full package of different scattering methods, but also optical microscopy using a confocal microscope and NMR to measure, for example, the diffusion of colloids or polymers. And in this way, our users get a full-scale characterization with complementary techniques. At Physical Chemistry in Lund, we not only have a perfect scientific infrastructure and a scientific environment that is ideal for you to conduct your experiments within EUSMI, we also have an environment that perfectly reflects the very well-developed work-life balance in Sweden and the relaxed atmosphere that you can find in this beautiful student city. I hope that I will be able to welcome you in the near future here as a EUSMI visitor, and I look forward to receiving your proposals. Welcome to EUSMI.